He's coming to us from Duke University, and he's an expert in ion-related quantum information science. So Sagnik actually started his career in India at the Indian Institute of Science and Technology, of Science Education and Research in Calcutta, where he was working on the fabrication of microstrip resonators. But he's also got a very broad background in quantum technologies. For example, he also worked at the Technical University in Dortmund in Germany on nitrogen vacancy centers. And so he got his master's from the ISA Calcutta in 2019. And then he went to the Joint Quantum Institute in Maryland. And there he was working on networking of ion-trapped quantum computers using photonic links. In 2021, his group, the group of his advisor, moved to Duke University, and so he moved along. And there he is developing photonic interconnects to scale up ion-trapped quantum computing. So the problem is, if you've got small quantum computers, how do you scale them up by using quantum links between them? So he's actually working in the group of Chris Monroe, which probably most of you know as the founder of IonQ, the quantum computing company IonQ, which made news just a couple of weeks ago because they're now opening a fabrication facility over near Seattle. And here's a number of very interesting projects. For example, one of the questions that you have is how can you actually trap a photon that an ion emits and then feed it into a fiber so that it can travel somewhere else? And they currently have got the record for the highest reported free space photon collection efficiency for quantum networking. Like how many of the photons that a single ion actually emits can you collect and then move through a fiber? So we're very excited that he is here today, and we get to hear from one of the really leading quantum computation ion trapping groups. It's a great pleasure. Please.
Thank you. Yeah, thanks, Peter, for inviting me here. I really like the drive from Spokane to Pullman. I drove here yesterday afternoon. So let's start with a bit of a detour. So when I was making this Colloquium talk, I was wondering what I should put as my cover slide. And then I came onto this AI large language model generates like pictures from text prompts. And I used this thing called DALL-E to generate this cover slide. And it's AI generated completely. And the prompt I put in was an impressionist painting of a photon, of an atom emitting a single photon with sigma or pi polarization. And this is what they came up with. I think it's really cool because it shows the atom and it shows the polarization of the photons that's coming out. You can see the pi and the sigma polarizations. I'll talk about this a bit later. I find the diagram the image really interesting, and it's pretty cool that an AI came up with this cover slide. I'm going to use this slide, I think, for all my future talks. Okay, so let's briefly motivate quantum computers and why and how they came about, who brought up the idea of quantum computers. If you look back in history, around 1980s or so, Feynman was toying with the idea of using, or basically, how do you simulate a quantum system efficiently? And there was this paper, or like a talk, I guess he gave in 1981, which is this paper called Simulating Physics with Computers. And in that paper, he was trying to look at a different kind of computer that is governed by the laws of quantum mechanics to simulate quantum systems, because as we all know that quantum systems, the Hilbert space of these systems grow exponentially as you increase the number of dimensions of the system. So a classical computer does not yet have an efficient way to simulate these systems. But if you were somehow able to harness the quantum properties of matter, if you can build a system which themselves obey quantum mechanics, you can somehow map that problem to something else which is also quantum mechanical in nature. And that's what Feynman proposed in the 80s. And nowadays, let me move that thing to the side. And now we have all these systems of atoms, ions, and electrons, all in different sorts of systems. You have NV centers, you have photonics systems, which have some intrinsic Hamiltonian in them. And you can tweak that Hamiltonian to represent some other system. to do some quantum simulation stuff. And we have recently been doing a lot of these studies. Our group in particular does also simulations stuff with ion trapping systems, but also there are other platforms where there's some interaction Hamiltonian and somehow map that into some other problem that you want to study. My talk is not going to be on simulation stuff. It's going to be on something called entanglement and how do you generate entanglement and how we can generate it very efficiently because we want to have entangled pairs across different chambers. So while I was making these slides, I came up into this interesting thing. So I was looking into the fact as to when was the first time that entanglement was observed. This is a simple Feynman diagram of an electron and a positron colliding, and you have two photons coming out. Because this system, in the system, there's no angular momentum exchange, so the net angular momentum of the photons coming out has to be 0, which is why the polarization of the qubits are entangled, it turns out. So if you can measure the polarization of the states of these photons, you'll be able to see that these photons are actually entangled. And the first such test of such, trying to probe entanglement and see its nature was done by Tiansheng Hu, who was a really famous, called the first lady of physics. She did this paper, it came out on the 1st of January, 1950, wherein she was observing these two photons that are coming out, and these are actually entangled in their polarization degree of freedom. Her main focus was working on parity violations in physics. I think she was unfortunately not awarded the Nobel Prize. I think her co-workers got the Nobel Prize on physics for parity violation, but she got a bunch of other very prestigious prizes, and she is considered one of the very pioneers of nuclear physics, experimental nuclear physics in particular. So the interesting thing to note is during that experiment, the total data taking lasted about 30 continuous hours that I've highlighted there. And the coincidence rates of these photons that are coming out from this scattering experiment was 4 per minute. And this is a completely uncontrolled system. You have this bunch of electrons and positrons flying around, and these photons coming out somewhere, and you map or you try to measure the photons of the states, and you get coincidence flicks at this specific rate, which is what I'll, I guess, compare with our work. So how far have we progressed in this 70 years? And we'll comment about that once we have some of our results. And of course, in 2022, we had the Nobel Prize in Physics shared along with Alan Aspect, John Closure, and Anton Zeilinger for experiments with entangled photons and doing Bell inequality violations with these photons, establishing that quantum is actually very different from classical systems because you have the Bell inequalities which are not not obeyed by classical systems. Anton Zeilinger has been pretty influential for me because I have read a lot of his papers, and we are actually going to do some of his experiments that he proposed several tens of years ago. So let's try to motivate some other reasons for quantum computers. One of the reasons is already I provided before when I was talking about Feynman. He wanted to simulate quantum systems. But there's also, you can also think of it in some other ways. One of this is the Moore's law bottleneck, which I think has already been hit in the last couple of years, couple of 5 or 10 years. So Moore's law basically says how many, what's the compute power and how does that change as a function of time? And it goes exponentially because in the in early stages, you could fit twice the number of transistors in a single chip. So you would roughly double the computational power every couple of years. But then as you were making these transistors smaller and smaller, you are bound to hit a limit where you have to make these transistors out of single atoms and molecules. And that, of course, will not work for classical computers because you need to have a definite state, whether it's a 0 or a 1 state, and you cannot do that with single atoms or photons because they themselves are quantum systems and they obey the law of quantum mechanics. And to scale beyond that, to follow this progress in compute power as we go further along in time, we need to be able to harness something else, which is quantum mechanics, to make these quantum computers. There's also the argument of complexity classes, and there has been at least one really good algorithm, the Shor's algorithm, which at least for now can factor prime numbers, which is till now there has not been any classical algorithms found for. That problem falls in the BQP class of problems called the bounded quantum polynomial time. Basically, if you have a problem and if you can find a solution for that, or you can find if the solution is correct. A classical computer can not find the solution of a problem, but it can verify it, which is what the Shor's algorithm is. So a quantum computer, given a quantum computer with lots of qubits, probably millions of qubits and probably hundreds of thousands of gates, you can prime factorize a very large prime number with the Shor's algorithm, which is not possible classically till now because that is a hard problem. So before we go into quantum computing or entanglement generation in general, let's quickly look at what the equivalent quantum bit is. So we know that a classical bit is either 0 or 1. It's in a defined state. And the state space of the system grows linearly as you increase the number of qubits. Quantum bit or a qubit, on the other hand, is a superposition of a 0 and 1. So you can represent the state of a single bit or a qubit as a superposition of the 0 and 1 states. And you can store a lot of possibilities. In fact, it's infinitely more possibilities because this state can be any linear combination of 0 and 1. And it's also more important, it's also a coherent superposition of 0 and 1. So it's not just 0 plus 1. It cannot be a mixed state. It has to be a coherent superposition of 0 and 1, meaning that the phase between the 0 and the 1 state has to be clearly defined and kept track of while you are doing quantum operations. Coming to gates, we have something equivalent for our quantum systems. We call quantum gates. There's an example of a gate here that I've shown. It's a C0 gate. You see on the left-hand side, the quantum gate, that's called a C0 gate. And on the right-hand side, you have the equivalent operator, which is an XOR gate in a classical computer. They do the same things, but one interesting property is that quantum gates are represented by unitary operators, meaning they're reversible. So you can undo a gate in principle, whereas classical gates, not all classical gates are reversible because sometimes specific gates have many-to-one mapping. Basically, you have two different or multiple different inputs producing the same output. So you don't know, given an output, you don't know where it came from. So it's sometimes irreversible in nature. Whereas for quantum computing, that's not the case. All the gates that we use are reversible in nature. That's a fundamental difference between the two systems. And what sets quantum computing apart from classical systems, I think, are basically because of these two properties. One is the ability to have a coherent superposition between 0 and 1, which is what I already told. So you can represent a state of a quantum system, a qubit, in a block sphere, and you represent it by two angles. So you need two coordinates to represent this position, a theta and a phi, and that precisely tells you what state it is in. So that is a coherent superposition of the state. And another important property is what I have been working on is entanglement. So entanglement is a way to have correlations between quantum particles, which are fundamentally different from the classical correlations that we have in classical systems. And you can create and entangle two atoms and then separate them far in space. And if they're entangled, you can measure different properties, which sets them apart from classical systems. They are not similar to each other in any sense. And quantum algorithm engineers or quantum algorithm scientists nowadays, they try to use these two properties to design their quantum algorithms so that you start with a bunch of qubits in a specific state and you let it evolve over time. And then you do these gates in between, which are somehow designed to destructively interfere the non-solutions, the solutions that you don't want, and constructively interfere the solution that you want. So you want to be able to design the algorithms using these two things that you have in your hand, these two things that are not possible in classical systems, to come up with the solutions that you want. And using this, you have the Shor's algorithm, which I guess he discovered to, for example, prime factor, which essentially relies on these things. So given now that we have a quick introduction of quantum computers, it's difficult to read, but yeah. So we have I have made like a slide of the systems that are there right now. This is from a science paper in 16. So it shows the natural qubits that we have on the left and the quantum, the synthetic qubits that we have on the right. So I work on atoms or ions, whereas there are other systems, they can use neutral atoms, for example, in a tweezer array, or you can have like photons, for example, or you can also make your own qubits by using, you can manufacture these, I guess they're called Colloquium systems. This is like a superconducting LC circuit that you can use to represent whether there's like, it's possible to have 1 unit of current or no unit of current, and that can be used as a quantum computer. And also there's other very exotic things like topological systems where they create some Majorana zero modes. I don't exactly know the details, but that's also a very interesting area of research. I will be working on or talking mostly about the trap ion system. And this is a very interesting system because of the fact that it has a very, very long coherence time. So you can define your qubit states in a specific basis where the lifetime of these qubits are really, really long. It maintains a superposition for really, really long. In fact, ions have been used to make optical clocks for some time. And the reason they are used for atomic clocks is that they have this really long coherence time, and that frequency splitting is very stable. We use ytterbium in our systems. I'll talk about it later. And it has a frequency splitting between the 0 and the 1 state separated by around 12.4 gigahertz. And that number is very precise. You can measure it to probably 12, 14 digits. And it is not sensitive to magnetic field of the first order. And because of that, it has a very long coherence time. And you can also, the other important things, not only do you need a good qubit, you also need to be able to perform good quantum gates on it. And I think right now, the best gates have 99.9x%, I think 99.94 or 95%. And people have been trying to make the gates even better. So for natural systems, ion traps, I think, are really good systems because they have the two things that you really need in a quantum system or a quantum computing system. That is a good superposition, there is a coherent state that can live long for a long time, and good quantum gates, which you naturally get in an ion trap system. And this is what one quantum computer looks like. This is a picture taken at the University of Maryland, and inside this box sits a vacuum chamber with a chip trap on it. This chip trap traps ions, and you shine some lasers on it, and those lasers perform some quantum gates on it. So if you were to open this box up, you'll see a vacuum chamber. Inside this vacuum chamber, you have a surface trap, and that trap looks something like this. It's a surface trap, and it's a zoomed-in image of a bunch of atoms trapped and fluorescing in light. Here you have 80 ions, ytterbium ions specifically. They're separated 4 microns, and they are around 100 microns above the surface of the trap. And you can hit all these atoms with a bunch of really tightly focused beams to perform manipulations or essentially gates. And your single atoms can represent a single quantum bit or a qubit. So how do you actually trap charged particles in a trap? And the answer is not that trivial. So Wolfgang and Paul came up with this trapping technique. It's called a Paul trap. Turns out that due to electromagnetism, it's actually impossible to trap a charged particle because of how electromagnetism works. The divergence of electric field in the absence of charges is 0. So you cannot, it's not possible to trap with a static electric field or charged particle. So the way you do it is you have to modulate the electric field somehow so that it creates an effective confining potential. So imagine you have a charge right here, and then you, by how electromagnetism is portrayed or defined, if you have a confining potential along one direction, the other dimension automatically becomes anti-confining. So you have to sort of keep on modulating it so that the particle somewhat stays in space. And this is what a Paul trap is. And what it looks like physically is something like this. This is a very fundamental, very simple design of a Paul trap. You have 4 rods there, and you ground 2 of the rods, and you put some oscillating voltage on the other 2 RF rods. And then you drive it at some frequency, and you also put some needles on it. And then what happens is at the end, these ions line up along the direction of weakest confinement. We usually put our voltage such that the direction of weakest confinement is along this axis. So naturally, there is a chain of ions that gets trapped here. And this is what I took a picture of this. I think this is one of our newest traps that we made. It has the 4 rods, and you see the needles in between, and you will get ions trapped in this small zone right there. Now that you have the atoms or the ions trapped in space in a trap, how do you perform gates on it, which is, I guess, the second ingredient for a quantum computer. And the way to do it is, I'll go over it very briefly because I'm not very aware with these details. I don't personally work on these things, but the general idea is that you shine 2 lasers on it. It's a 350 nanometer mode locked laser, and that effectively introduces an Ising gate, but it gives a phase shift to only 2 of these states. So if you have a spin down, spin up, or a spin up, spin down, it gets a phase phi equal to this number. If you want a full entangled state between these 2, you need to set the phase phi such that it's pi over 2. So you drive it for a specific amount of time, and then at the end of the gate, you will have these 2 particles that you want to entangle together at the end of the gate. And this is what is called the Ising gate. Effectively, it's an excess interaction between 2 atoms from the laser beams. So I have briefly described, motivated, and seen what these quantum computers look like. And let me go a bit into a different direction as to what my research interests are. So to motivate that, I'm going to talk about something about scaling. So we already have traps where you can store tens of qubits. You can operate with them with tens of qubits, probably maybe even 50 qubits or 100 qubits. But at some point, the problem is that if you trap a single chain together, there is too many ions in one trap, and it gets a lot of problems because it starts heating up. If you want to do a gate, you need to address them really well. You cannot do that if there's too many ions. And there's also the problem of motional mode crowding, which is what one way of saying is, if you have too many ions in one trap, they are basically a quantum harmonic oscillator system, and you have these modes that are really close together. And if you want to do this quantum gates, you need to address the motional modes, because that's what we use to drive our XX interaction gates. So in short, it's bad to have long chains of atoms. So the way, I guess, to go around it is to divide it up into smaller chains. And then you can imagine you have a trap which has multiple zones. So there are smaller chains of smaller atoms. And then you entangle, let's say, specific pairs at one time. Let's say you entangle here or here. And once that is done, you move it to some other zone, and you do a lot of shuttling of atoms in a single chip. But again, the problem is you can only go so far. You can fit only a certain number of particles in a given trap. So at some point, you need to move into an architecture wherein you have separate traps and you entangle. Another reason why this architecture of just moving around atoms is that it is sort of inefficient. So this was a paper in 2023 by the quantum computing group Continuum, and they published this result. And from here, you see around 1% of the time you're actually doing quantum operations. The rest of the time is spent doing cooling of the ions or transporting the atoms from one place to another. So as you see, it's like really inefficient. Most of the time, you are not really doing any quantum computing stuff because you have to move atoms around, which takes a long time. So here comes the sort of thing that I work on, which is how do you connect these several chips, which are in several ion trap modules together. And a rough, in general, like an overview of that would be something like this. This is what a quantum computer might look like in 10 years, 20 years. So you have these ion trap modules, which emit photons. And you connect all these photons into a N-by-N optical cross-connect switch. So you can basically have any photon coming from any pair and any other photon coming from some other chip, and you basically take them out and it goes in through a beam splitter, and then you do some detection on them. And if you get the right pattern of detections at the end, you project the ions in these specific traps to an entangled state. And that's where I work on. A model of such a system is given by this. So a very rough overview. You can imagine some memory qubits where you store information and do your quantum computing on, and you have your communication qubits, which is used to entangle or send out these photons and entangle these photons because they operate at a different wavelength. So to be more specific, let me go a bit into the details. So this is one way of doing it. So ytterbium is a good memory qubit. It is not sensitive to magnetic field, which is what makes it good. So you store these ytterbium atoms in single chips and you perform quantum computing operations with them. However, ytterbium does not emit visible light. It emits in the UV spectrum. So you need some other species to basically couple it into a fiber, because fiber technologies are easy. They're available. There's lots of technologies already developed for fibers. So try to find some other atom species or ions which emit in the visible. And this barium is a good species because it emits in visible. It's 493 nanometers long. I mean, I have a list of all the atoms emitting in different. There's a group 2 atoms, and barium has the longest wavelength by far. So you select this specific species and you trap barium and ytterbium in the same chain together, and you perform your communication with barium atoms. And once you can entangle, let's say you entangle this one and this one together, you have an entangled barium ions, and then you can swap the entanglement to your memory qubits by performing local gates on them. So this is one way to scale up quantum computers more in detail. So given that I work with barium energy, barium ions, there's a quick energy diagram for you guys. So you have the S half and the P half level. They are the main transition that we cool on. So it's 493 nanometers. There's also this D3 half level. So that's connected by a 650 nanometer laser. And this form a closed loop. We have S half and D3 half. So you can shine 493 and 650 together, and the ion starts fluorescing. It starts emitting blue light, or sorry, green light. And that's basically our fluorescence, or how you generate photons from them. I'm going to talk more about that later. Our qubit subspace is actually in this S half manifold. So S half, when you have a magnetic field, it splits up into 2 parts. It has a MS equals to plus half and a MS equals to minus half states. And that is where we do our computing stuff on. We define our Zeeman qubits to be our quantum computing qubits. We also have this other laser, which is very important to our operations, which is this this laser which connects the S half to the D5 half level. The 1762 nanometer laser. It's a very small line width laser. It's a really narrow laser, and it can selectively select out the plus half state or the minus half state. So you can either shelve or take atoms from the plus half level or the minus half level. You can put it in the 3-5 half level, and it has actually quite some importance, which I'll go over later. And I have a slide on the 762 laser. It's smaller than 300 hertz line width that we measure, and it's used for shelving detection. And how that works is basically, let's say you have a 0 qubit and a 1 qubit. So these are the Zeeman qubits that you have there. And you want to see if your ion is 0 or 1. So you can shelve one of the states. So let's say you shelve this one up there. So 0 sits in the D5 half, and it has a really long lifetime. It can sit there for up to 30 seconds. That's the lifetime of that state. So once you put that put that ion up in the D5 half manifold, you can fluoresce your 493 and 650 nanometer light. And if you see photons emitting, that means that the ion was probably in the 1 state. And if you see dark, that means that it was in the 0 state. And that's how you distinguish between your 0 and 1 state. So by selectively shelving one of the states and followed by detection by fluorescing that. So a bright would give you a 1 state, and a dark would give you a bright state, a 0 state. And we can do that with really high fidelities. So 99.6% of the times we prepare dark, we measure dark. And 99.7% of the times we prepare bright, we measure it to be bright. And that's a really, really good state preparation and measurement. So before we dive into more details, I wanted to show you guys some pictures. you guys know that I had to move entire lab in the middle of grad school. So I joined Chris's lab, and then I know of the fact that I think in a month or so, Chris informed the group that our lab is moving. And I was very surprised by that, also terrified. But I think the move went decently well. It did take some time, but I think it taught me a lot of things because we had to set up the entire lab from scratch. So I basically know all the intricacies that goes on in a lab like this. Chris, in fact, actually helped move our chambers. You can see all the 5 chambers that we had at that point. I think one of the chambers we left behind at UMD, but he rented out a big van and put all the chambers in one van, and he personally drove the vehicle from UMD to Duke. And on 2021, we had all these tables completely empty. We put some chambers on it that we got from UMD. And right now, one of the chambers looks like this. So we have these 3 nodes that we work on. This is one system here, Alice, capable of trapping charged particles. And there's 2 more, Bob and Cleo, which also trap barium ions. So it's basically a 3-node quantum system. You have 3 ion trapping systems, and the idea is how to entangle these 3 different chambers. So let's get into some detail about how these ion photon entanglements work. So imagine you have an atom here, and you set the magnetic field along this axis. And if you decompose the way it emits out light, you see that there's a sigma channel of decay and a pi channel. So the sigma photons are circularly polarized, the pi photons are linearly polarized. And if you collect perpendicular to the magnetic field, you can project the sigma plus into a horizontally polarized photon, and the pi light into a vertically polarized photon. So just reiterating, so this is the level structure for barium. You have an S-half state here with the down and the up spin. If you can somehow excite to this p-half state somewhere, it can decay either into the down state or into the up state. And depending upon where it decays in, either the down or the up, it can create a sigma or a pi polarization. At the end of it, you have an ion photon entangled. So to be even more precise, so we pump all our atoms into the 0 state in the beginning, and then you excite with a 493 nanometer sigma polarized light for a couple of picoseconds. Once it's up there, it's going to emit either to the 0 state or to the 1 state. But again, this transition is sigma, so it emits a sigma plus photon. And this transition is a pi, so it emits a pi photon. So at the end, you have this ion photon state, but once you collect it into a fiber, you get effectively the state of this one, a 0H plus 1B. So this is an entangled ion photon state. Once you have this state, you can do something as follows. You can capture these 2 photons. So let's say you have 2 chambers, Alice and Bob. You excite them to the p-half level, as we showed as I showed before, and you capture these 2 photons. And if you bring them into a beam splitter, at the end, it goes through some PBS, some polarizing beam splitters, and you can observe some clicks with the single photon detectors, otherwise also known as the APDs, avalanche photodiodes. So a specific click pattern at the end of the experiment can project your atoms into an entangled state. So for example, if you detect 2 photons, 1 photon in 1 and 1 photon in 2, you have got 1 H photon because a PBS reflects H photon, and you've got 1 photon in 2 because a PBS transmits a V photon, but you don't know which path that photon came from. So H could have come from either this chamber or it could have come from this chamber. The beam splitter basically erased the which path information. So at the end, you know that either this ion is in the 0 state and this is in the 1 state, or this was in the 1 state and this was in the 0 state. So you effectively get an entangled state. So it's either 0, 1 plus 1, 0, or 0 and 1 or minus 1, 0, depending upon the specific click patterns in there. And this is one of the schemes we use for generating entanglement. So for our, I think I showed a slide before with all the 3 chambers. We have our new chamber that was part of building. We call it chamber C or Cleo. And the interesting thing is that this chamber has A spheres or lenses inside the vacuum chamber. So this is what it looks like. So you have the photon trapped here, you have the atom or the ion trapped in here, and then these A spheres live inside the vacuum chamber, and these are mounted on specific piezos, which are also inside the vacuum chambers. And these things can move around. You can collect a lot of photons because the distance between the ion and the A sphere is around 6 millimeters, and that allows you to have a high numerical aperture, 0.8 numerical 0.8 Na, and that basically collects 20% of the photons from each side. So effectively, you are collecting 40% of all the photons which are being spontaneously emitted by the atom. Just something for scale, our 4 rods are separated by a millimeter in this direction and half a millimeter in this direction. Our ion sits in the middle. So once you have this ion photon state, you want to be able to perform some measurements on it. And what people usually do for ion photon entangled states is to perform this measurement called a correlation and coherence measurement. And a correlation measurement is basically asking the question that if you have a H photon or you detect a V photon, what's the probability that the ion is in 0 or 1? So how well are the ions and the photons correlated together? And if you turn the state of the photon by using some half-wave split, you see that ions are also rotating their state. So you scan some half-wave split angle and you'll see that the ion actually moves from being in the up state to the down state and vice versa. And that shows that basically that these ions and the photons are correlated together. You can also perform some coherence measurements, which is instead of rotating the photon, you rotate the ion by using some microwaves, or in our case, we use a Raman gate or a Raman pulse or a Raman laser, and that drives basically rotations for the ions. And you see these really good flops. And from this, we got ion photon fidelities to be around 99, 98%. Once we had Clio or the new chamber, we wanted to test how good that chamber is. So we had this interesting experiment. So we trap basically 2 atoms together in one chamber, and you center one of your A spheres on one ion and the other A sphere on the other ion. You could always do a very simple gate because they're in the same chain. You can just do a gate to entangle them, but we did the very complex thing of collecting a single photon from one atom through this A sphere and another photon from this atom through this A sphere, and then you bring these photons together into a beam splitter, and you do the same, you do the protocol that I told you before, and that basically projects these 2 atoms, which are actually close by in the same trap, to be entangled. And this is what our experimental scheme looks like. You do Doppler cooling for 100 microseconds, and you have to do this entangling attempts on these atoms. So you excite both of them together, and you collect photons from each of them, and you see what kind of click patterns you get in your APDs. And you repeat it a bunch of times, and you see how many number of photons you get and what those fidelities are. In each of this entanglement sequence, you have this sequence, which is you basically pump. I told you about this before. So there's a latency of the AOs to turn on, about 4 nanoseconds. You pump for around 3 nanoseconds, and you excite, and you collect these 2 photons. And hopefully, both the ions get excited and they fall down. You capture both these photons and you bring it into a beam splitter and you measure them, and that projects it into an entangled state. So for this experiment, we expected, given our collection efficiencies and our losses in the entire system, we expected an entanglement rate of 200 per second. However, we measured only around 80 per second with a fidelity of around 94%. And the reason why it was a bit slow is because the ions were getting heated up. So when you excite the ion with this excitation pulse, it heats up the ion. And once you heat up the ions, the fiber coupling, so you fiber couple the photons, that the fiber coupling gets lost. So to get around that, what we did was basically sympathetic cooling. So we trapped 2 barium atoms and 1 ytterbium, 2 barium atoms and 1 ytterbium atom. And you cool the ytterbium atom. So the ytterbium atom is sympathetically cools the barium atoms. So you can keep on entangling using the barium ions. And the ytterbium ion is basically pumping out all the heat. So you can keep on entangling without losing rate. And with that, we got an entanglement rate of around 250 per second, which is, I believe, the highest rate of entanglement generation between any two spatially separated quantum network nodes. And you can see actually the effect of heating. So if you have very strong ytterbium cooling, the success probability goes down, but it stabilizes to a specific value as you increase the number of attempts. Whereas with no cooling, it drops a lot. So you can see how a cooling atom helps you increase the rate because it basically helps you in cooling. So you can keep on entangling for longer and longer durations. So this plot is, I forgot to put the references for all of this, but I can, if someone wants to know, I can give you the references. But this is a plot of the current status of rates and fidelity. So you have all these systems, ions, atoms in these quantum dots, trying to generate quantum entanglement between separated chambers. And you see our work is up there. So we got the highest rate, and we are also pretty high in terms of fidelity. And I think this is a really good result for trapped ions in demonstrating that you can have really good rates and get really good fidelities, which is actually essential to scaling up quantum computers. One problem with using polarizations as qubits is that once you have these photons passing through different optical elements, you can transform this sigma and pi photons into something else. So you have a channel for polarization errors. So as you can see from the error budget here, the polarization errors are around 3% as we estimated. So if you want to go up in fidelity, you have to cancel out these polarization errors. And the way to do that is to basically work with one polarization. So we have this new scheme of doing entanglement, which uses basically a specific polarization. And this was a protocol sometime back by Barrett and Koch. And the protocol is quite simple. Instead of encoding the information of the qubits in terms of the polarization of the photons, you encode it in terms of the time of the photons. So a photon can be either in an early time band, it can be early, or it can be late. So if you have good timing resolution capabilities on your detectors, you can do the same trick that we did with the beam splitters, but instead of the photonic information being stored in the polarization, you store it in the timing of the qubits. And this is what it looks like. So you have two atoms, and a time band can be in the early or the late stage, same as before. And once you do that, your detector can be, you can trigger to be either in the late and the early or the early and the late. And that basically projects your ions also in a 0, 1, plus, minus 1, 0 state. And this was also a protocol that Barrett and Koch came up with during 2000s. And most of the systems nowadays, InvisiCenter systems, some quantum dot systems, they use this protocol to generate entanglement. This is robust to photon loss. And also if you send the photons through very long fibers, these photons can, there might be some polarization dependent loss on the fibers. You mitigate all of that because you're working with only a single polarization. And an implementation of that looks something like this. So you have, instead of storing the qubits in the Zeeman states of the plus and minus half, you store it in the optical state. So you store your down qubit or the spin down in the SF manifold. You store your spin up qubit in the D5F manifold. And you do a pi/2 pulse, a 7-in-6 driven by a 7-in-62 laser, a pi/2 pulse on these two, and you excite between this state and to the P state and let it fall down. So it can get excited. So if the atom was here, it would have been excited and you collect only along this axis. And then you do another pi pulse on the same transition and you excite again. Because you started with the superposition of the down and the up state, that means the photons would arrive, or depending upon if the atom was in the down or the up state, your photons would arrive either in the early or the late time band. And once you do that, you basically have the same phenomena happening as the H and V. You instead replace the H and V with the early and late. And if you detect 2 clicks with one in the early and one in the late. You don't know if it came from the ion on the left or the ion on the right. So it can be either 0, 1, plus 1, and then you have the same thing. So you project the ions into an entangled state as well. So this is some very preliminary results. So this is the first time we got using time winds to generate entangled states at least in the ion platform. And this is some data that we took just last week. It's also really good time because I can show this data now. So this is basically, you can see the suppression, the HOM suppression. HOM stands for the Hong-Mandel interference. It basically says that if you have two identical photons coming in at the same time into a beam splitter, they'll always bunch together. They'll always come out of the same ports. So you see that when these photons are in the same beam, if they're both early or late photons, they bunch together and they don't come out of the same ports. But you see a lot of late early and early late photons. And you also generate entangled states. So this is very preliminary data, but we get an entangled state with a fidelity of around 80%. We are going to work on it more and hopefully try to get to a world record fidelity in terms of entangling operations and see how much we can really push up this number high. And then I guess I'll talk a bit about some higher dimensional entangled states. So these are one of the proposals by Anton Zeilinger, as I told you about. So you have basically 2 PBSs and you have 3 entry ports into the PBSs. And if you detect a specific click pattern, you can project your ions into a 3-ion entangled state. It's called a GHZ state. It looks something like this. The 0, 0, 0, plus minus 1, 1, 1 state. And the protocol involves collecting photons from each of these chambers. And then you pass it through a bunch of PBSs and beam splitters. And you detect it and then given a specific pattern, if you detect a specific pattern, you project it into a GHZ state. Our rate would be really low, around 0.2 per second or 1 per second maybe. But this is a really cool set to observe because GHZ has all sorts of interesting correlations that you can do. There's a Mermin inequality in physics, which is obeyed by these states. So you can see that, okay, quantum mechanics actually works. I mean, we already know it works, but it's always cool to have these experiments to see it actually. And then also in the future, we have experiments lined up, which basically tries to use the middle chamber, which is Clio, to be used as a quantum repeater. So a quantum repeater is something that distributes entanglement over long distances. So you need to be able to place some repeating devices in between, which can basically help you generate entangled states over long distances. Because if you just transmit photons into fibers, they have really high losses. So you need to be able to have some device in the middle which can sort of like amplify the signal in between. So a quantum repeater in some sense does that. It will basically help us to generate entangled states over longer and long distances. And this can show us that, if you use a quantum repeater, that there is some rate gain that you can have over using a single link between Alice and Bob. And with that, I will briefly point out some small numbers. So like 70 years ago, when Sheng Wu came up with this experiment that was completely spontaneous, it's a completely uncontrolled experiment. They had observed positons and electrons colliding to get these entangled photon pairs. And it was completely uncontrolled. You have these things coming together, they're colliding somewhere, and these photons coming out somewhere. And that was obtained at a rate of around 4 per minute. And now we have these completely controlled systems. We can store it in space. They're trapped in a specific point in space, and you excite them, and you can generate entanglements with around 200 or hundreds per second. So this is what we have gone in the 70 years. So with that, I'll skip this one. With that, I'll thank all my team members in the iPhoton team, Misha, Isabella, Ashrit, Jameson, and Ashish and George. Also thanks to Chris and all the funding agencies. So thanks for listening to me.
Very nice and fascinating insight. Great job. Time for questions.
Which is sort of a basic question that I'm sure you answered at the beginning. But when you're doing your excitation of two separate, do you have to then be careful to have a split single photon?
Yes.
You do.
Yeah, so you basically split it with the 5. So you have a single excitation pulse which travels to both the atoms. But it doesn't matter. What we really want is to be able to excite from the ground state to the excited state. Once it's up there, it's going to emit spontaneously. And we use the polarization degree of freedom that's contained in the photon to entangle them. So it doesn't, we just need to be able to excite it at the same time so that the photons come down at the same time.
So there's not a lot of strict, you're not going to be very careful about.
No, I don't think so.
It doesn't have to be like a single photon.
No, the only thing that matters is that these two excitation pulses come in at the same time, so that the photons that are emitted are also temporarily matched when they're emitted.
But there can be many photons in the pulse.
Yes.
So you had one graph following up on this where you had the success probability of generating those were just 10 to the -4 or something, right?
Yeah.
So that means you say the entanglement generation is controlled, but there's still some aspect of randomness when it succeeds and when it doesn't,
Yes.
right?
So it's a Heraldic protocol. It's completely probabilistic. So you need to be, so it's a, if you go to the rate slide, so roughly the rate, the entangled rate goes as half times repetition rate times p squared. So this p squared is the collection probability, or what's the probability that you excite it and you get a photon out. So it goes as the p of both the chambers. So it's a p from the first chamber and a p from the second chamber. And you multiply by how fast you can do this experiment, which is the repetition cycle experiment, which is around a megahertz. We can run this at a 1 megahertz. It's half, because you detect only half the Bell states at the end of the experiment. So you get from this number around 200 per second.
Any further questions?
One more quick, very quick.
Sure.
Mundane, in your surface traps, it looks like you don't have a regular spacing.
Yes. Yeah.
It's the spacing changes.
Yes.
Okay, even in the surface trap.
So for surface traps, they do a lot of complicated stuff with the potentials. So usually we have x squared potential, just like quadratic traps. But surface traps, they put in a bunch of DC electrodes on the surface to make it more of a flatter profile. So it has a x to the power 4 component. It's a quartic trap, so it's more flatter. And the reason you do that is that you have to be. It's good to have equal splittings on the atoms. You don't see it in this picture because they trap a lot of ions, but we don't usually work with 80 ions. We work with around 20 or 30 ions, and usually in those systems, they're all equally spaced.
Pretty well.
Yes.
Not exactly, but pretty well.
Yes, and we need to be able to do that because we are doing individual addressing of these atoms. So we want to shine laser beams on them.
Yeah.
So it is important that they are equally spaced.
And that you're doing the single AOM by 23 frequencies.
Yes. Yeah.
That's and have to worry about all the crosstalk.
Yes.
Yeah. Did you know that out?
I'm not sure what the crosstalk levels are.
Yeah.
That's a different group that works on these specific techniques. But yeah, there's a lot of things that goes on to make sure that there's enough crosstalk.
Yeah. Scott,
yeah. So I was just maybe you glossed over really quickly. I was not totally convinced on why the barium needs to be there in your experiments. Like, it couples to the ytterbium atoms, but I'm not sure about why.
Oh yeah.
Exactly.
So if you just have two barium atoms, what we were doing before, two barium atoms in the same trap, and you keep on exciting it. So you go to this, let's go to the slide where there's this experimental protocol. So you see that a bunch of the time is spent on cooling the atoms. That means you are not doing any entanglement attempts, right? So that's a lot of time that you're not really doing anything. So if you can remove this step, which is what we do by introducing another species, ytterbium. So that is a different species, so it talks to different wavelength lasers, and that doesn't mix up the barium state. So you can pull the ytterbium atom and keep your entanglement atoms on the barium atom. So that basically helps you to shrink down this window, so to the point that we don't have to cool at all. The ytterbium does all the cooling.
You have the ytterbium in the middle between the two bariums?
On the side.
On one side of the different.
Yes, yeah. And there is one reason for that, because we don't want the things to swap in place. So for ytterbium to be on the one side, there's only one possible configuration. So it's less likely that it will move around. But if it's in the middle, it can be like middle, but then the barium atoms are on the two sides, but they can flip together.
I see.
So we just keep it on the side.
Yeah.
It's also very, we don't like working with a setup because the ions actually keep on flipping around. We have to swap the data. But essentially what that helps us to do is basically shrink down this cooling window to really small. And then you can keep on entangling for a really long time without.
Okay, so maybe we have to come to an end here, but you can come downstairs and discuss more. Let's thank you again for a fascinating talk.